Hello, and welcome to PROKON's YouTube channel. My name is Andrew Brooks. This video contains an extract from the Class 4 Members in Compression webinar, originally hosted on the 15th of July 2021. When we design steel members, we need to consider both the overall behavior of the member as well as the local buckling of the member section. Standard sections are usually hot rolled sections, and the section's webs and flanges tend to be slender. This means that, subjected to loading, it is possible for the flanges or the webs to buckle. In certain cases, it is possible that the local buckling can occur before the yield stress is developed in the section. These sections are referred to as Class 4 sections. The various design codes use section classifications to take the local buckling of sections into account. Although the terminology is a bit different in each code, the same phenomenon is addressed. The Eurocode and codes derived from the British design codes classify sections as Class 1, 2, 3 or Class 4 sections, whereas codes from Australia and the US, their classification refers to compact, non-compact, or slender element cross-sections, where the slender element cross-section is similar to the Class 4 sections. These classifications are based on the section's susceptibility to local buckling, and classification is done according to the ratios of the element's widths and thicknesses. So what do these classifications actually mean? For a Class 1 section in bending, the plastic moment can be obtained and the section has a high rotation capacity before local buckling will occur. A Class 2 section in bending, the plastic moment can be obtained, but limited rotation capacity means that local buckling will occur with excessive rotation. For Class 3 sections, the yield moment can be obtained, as they say, at the outermost fibers of the section, but local buckling prevents the section from reaching the full plastic moment. And for Class 4 sections, local buckling will occur even before the yield moment is reached. Now we narrow down the discussion to a Class 4 member in pure compression. We can plot the maximum stress against the slenderness of a column to obtain a graph that looks something like this. The Euler buckling curve shows under which load the column will undergo global buckling, and the yield stress line shows at which slenderness the failure is governed by the yield stress. The intersection of these two lines is quite important. All elements to the right will fail due to global buckling, and elements to the left, their failure is governed by the yield stress. However, Class 4 sections can't reach the yield stress on account of local buckling. There is quite a good chance that compression elements fall within the range of this red square on the screen. For example, when designing trusses, the vertical and diagonal elements will most likely be elements with low slenderness values. Popular elements in trusses are angles and T-sections, many of which are indeed Class 4 sections. So how do we design elements where the yield stress governs, but the yield stress can't be reached? To deal with this, there are two options available to us. The first is to calculate an effective area and use this new area in the design. The second alternative is to calculate an effective yield stress and design the section as a Class 3 member. although the first alternative, the calculation of an effective area, seems to be the most prevalent approach, and the approach is used in STRAT. This shouldn't be any news to you. As engineers, we have been taught this. What might be new is how PROKON deals with the class 4 elements in compression. The best way to show this is with an example. The reason for this example is that it comes from the South African Steel Construction Handbook, or the Red Book as it is more commonly known. This example is example number 4.2 in the Red Book, and it is a published example so that we have something to compare the results of STRAT to. The purpose of this example is to calculate the maximum capacity of 150 by 10 equal angle. The example's result is a maximum compressive resistance of 533 kilonewtons. But according to STRAT's detailed equations, the maximum compressive resistance is 551 kilonewtons. This is a bit of a jump, and let's see why. If you were to trace the calculations done in both the Red Book and in STRAT, you'll notice that the results diverge from each other after calculating the elastic critical buckling stress. But up to this point, the calculations are fairly equal. A minor note, the Red Book assumes the warping torsional constant to be 0, which is okay since the factor plays a minor role in the ultimate compressive resistance compared to the work it takes to calculate the value. STRAT makes no such assumption, and therefore the critical stress is slightly higher. Let's pause the example for a brief moment and consider what this elastic critical buckling stress is. Remember the buckling curve in the previous slides? This elastic critical buckling stress is a reduced stress that can be used to do the design. It may be governed by flexural buckling or by torsional flexural buckling. The weaker of the two stresses is calculated according to the specific design code. The buckling behavior depends on the profile shape and the slenderness of the element. Back to the example at hand, the critical buckling stress is the minimum between the calculated flexural buckling stress and flexural torsional buckling stress. For this angle, the critical component is the flexural torsional buckling. If this were a class 1, 2 or class 3 section, we could simply multiply the critical buckling stress by the sectional area and the material factor to calculate the answer that we are looking for. But since this is a class 4 section, we need to do some additional work, and that is to calculate the section's effective area. The Red Book's process is quite straightforward. The effective area calculation is applied, and the compressive resistance is calculated in one step. In STRAT, however, the effective area and compressive resistance is noticeably different. Because the sectional area is adjusted, the critical buckling stress theoretically changes as well. STRAT considers this and iteratively calculates a new effective area and effective critical buckling stress. Since the sectional area has changed, the critical buckling stress also changes, and then the sectional area is once again affected by this new critical buckling stress. STRAT's results can be plotted for a succession of iterations. The initial sectional area is equal to the gross area of 2,930 square millimeters. After the first iteration, the area drops to 2,630 square millimeters, which is the value that the Red Book uses. If the iteration continues, the results stabilize or converge to a final answer very quickly. After the third iteration, we just about settle on an effective area of 2,700 square millimeters. And that's the reason that Strut calculates an increased compressive resistance for a Class 4 section. Thank you for watching. Please remember to subscribe to PROKON's YouTube channel.